this event is organised through the Network Plus for the decarbonisation of heating and cooling as part of a series looking at the different challenges of decarbonising our heating and cooling sectors. This month, delighted to welcome a presentation covering research taking place at Warwick University. Dr. Ángeles Rivero Pacho, who is an assistant professor at the University of Warwick. Ángeles holds a PhD in mechanical engineering from Warwick University and since 2019 has been working in the program grant LOTNET, which in real language means Low Temperature Heat Recovery and Distribution Network Technologies. Her two main research areas are sorption heating and cooling technologies, as well as data analysis and modeling of energy systems. So her presentation will cover her work in developing a detailed case study on the efficient heating provision for a group of University of Warwick buildings called SmartSquare. So
thank you for the introduction and for giving me this space to talk about my project. And so I have this presentation and it's divided in like 3 parts. I thought I could introduce a bit what LOTNET is, then my project, and then talk about a bit more about my research group at Warwick, if I have time. So yeah, as you said, LOTNET, Low Temperature Heat Recovery and Distribution Network Technologies. So this project is a £5.5 million project funded by EPSRC. We started into 2019 and is supposed to be running for 6 years. And basically we use low temperature heat distribution networks, and we want to integrate waste heat from industry and from other sources, such as, for example, London Underground, commercial supermarkets, from industry and data center. And we want to integrate all that waste heat. We want to use renewable energies as well. We use as well rivers, like heat from the environment, such as rivers, ground air, and lakes. And we want to provide heating and cooling for domestic or industrial applications, incorporating technologies such as heat pumps, thermal heat storage, such latent heat or thermochemical, and thermal transformers, organic ranking cycles. So it's quite a big project, and we have 4 universities working on it. So we have, at Warwick, we have the School of Engineering. So we have expertise in heat pump technologies, sorption materials, energy transformation. And we have as well the business school, excuse me, that, they help with business cases. And as well, they look into behavioral change when adopting these technologies. We have Loughborough. They have the Center for Renewable Energy Systems. They look at renewable energies, storage systems, design of energy efficient products. And as well, they have the design school, and they provide consumer interaction research and consumer behavior in order to implement these new technologies. Then we have Ulster University. Their expertise is vapor compression heat pumps, organic racking cycles, and as well demand side management. And we have London South Bank University. Their main expertise is cooling. They also been working recently in smart local energy systems, and they run as well the network CIRAC, which is a dissemination network. I'm going to talk about it in the next slide. So as part of LOTNET, we have 2 dissemination networks. We have Knowledge Exchange Network for early career researchers. We organize seminars, webinars, and we also try to establish links with sister projects. And we have CIRAC, which is part of as well of the Institute of Refrigeration, and is sustainable innovation in refrigeration, air conditioning, and heat pumps. And they organize webinars or meetings, talks. It used to be in person, then we went webinars during COVID, and now they started having them in person again. So they choose universities or industries. We have a meeting there. There are some presentations, some networking sessions, and there is always a tour of the facilities of the venue. And just to mention, the last one happened in Glasgow, in the Queen's Quay Energy Centre. And there is video recording. So if you go to the website, you are going to see all the events that happened and the ones that, the future events. And it's all free to attend. You just need to register. So information about LoTNet after my presentation, if you want to contact any of the academics, if you want to see publications, papers, conference papers, or project updates, please go to the website. And so the research challenges that LoTNet has, we have 5. So I'm going to explain one by one. So the first one is to develop a spatial and temporal dynamic simulation that is going to be modeling dwellings, and it's going to be modeling how renewable energies can be integrated in order to obtain a net zero energy system. And this has been done by Loughborough, and I'm going to talk a bit more in the next slides. Then we have advanced performance of novel thermal storage, distribution, and capture. So for example, here we have distribution medium. So this is work that I did in the past. So I looked into thermochemical heat distribution networks. And we collaborated with London South Bank in order to maybe integrate an ambient loop of this material in an energy system. Then Loughborough has been doing research in storage, latent heat, thermochemical, and London South Bank been looking into potential sources of waste heat, how to capture them, and the amount of waste heat that could be available from these different sources. Research challenge 3 is to advance performance of energy transformation technologies. So we have Ulster University, they've been doing a lot of work in vapor compression, heat pumps, and organic racking cycles for high temperatures and for as well lower temperatures but higher COPs. And at Warwick here, we've been working with thermal transformers. And the last, well, not the last, but the 4th research challenge has been looking into the consumers, how they will adopt these new technologies, and as well the business requirements for the adoption of these new technologies. The 5th challenge is to integrate all the previous work, and this is going to be done towards the end of the project. So we also have, in order to use all these developments, technologies, and modeling into try to use them in real life, we've been developing case studies. So we have 3. So one of them is the one I'm going to talk about, it's the one I'm working in. But the first one is related with London South Bank in London. So they've been working with a smart local energy system in the borough of Islington. The project is called Green Skies. And basically they're working with the 5th generation ambient temperature heat network loop. So basically they want to integrate in this network waste heat coming from the London Underground, waste heat coming from data centers around the city, boreholes that connect to the London aquifer. They integrate as well solar energy, renewable energy, PV, and they integrate as well electrical vehicles. One of their schemes is the New River scheme. And as I mentioned, they are integrating cooling, heating, mobility, and power. Taking into account heat pumps, electrical vehicles, they are measuring the benefits as carbon savings and as well as running costs. And as well, they are developing a control system. I think they're going to be using artificial intelligence to have everything under control. And they are working as well to expand and have some other smart local energy systems. One could be developed in Sandbourne, West Midlands, and another one in Barnsley in Sheffield City. The second case study corresponds to Loughborough Town. So that model simulation that I presented earlier that they are developing at Loughborough Uni, they want to, basically they want to use it to predict a net zero heating provision for the town of Loughborough. Loughborough Town, they have 23,000 dwellings, building types, and they have a population of 67,000 people. So they look at different populations in many towns in the UK, and basically what they want to do is see what the sizes of the towns are and see how this tool can be implemented to other towns and see if to use it to achieve net zero, basically. So if this tool is used in other towns, this can reach 32.6 million people in the UK, or England and Wales. Also, because of the size Loughborough has, it can be divided into regions. So different regions can be analyzed differently and maybe then integrate together. So basically, just saying that this tool can be scalable, different sizes. So they've been, as I said earlier, mentioned, they've been integrating renewable energies such as photovoltaics, wind, and they have thermal stores, different sizes, different temperatures. So all these variables are going to be explored. I guess it's an ongoing process. The modeling will be refined for greater temporal and spatial resolution, and different operational strategies are going to be developed as well. And they're going to integrate as well more information regarding the buildings, the thermal mass, the fabrics of the buildings, the UA values. As well, they're going to take into account network operation temperatures, maybe can be constant or variable depending on the time of the year, depending as well on the waste heat sources available in the area. That's another thing that needs to be assessed. And as well, new heat generation technologies that are being developed at the moment can be integrated. We have a model of the new technologies that can be integrated in the simulation tool. And storage, depending on where they go, the size of them, the type of storage that they have, is going to be assessed, the costs and the CO2 emission reductions. Also, as well, electrification of transport is going to be added as well in the future. And the third case study is the University of Warwick one. So basically, we are looking at the campus, the Warwick campus, and we are using it as to analyze and then implement new technologies. Basically, we want to achieve net zero, and we are looking at replacing, I guess, the heat provision that we have at the moment is done by combined heat and power engines and boilers. So we want to replace those with heat pumps, vapor compression heat pumps. So as we can see, there are a few projects running in parallel at the moment. So we have Energy 2020. So it's a it's a heat network delivery unit study. And yeah, they want to achieve low zero carbon heating across campus. And then we have SmartSquare, which is the one I'm working in. We are working as well with building management companies to monitor better the buildings and maybe include different strategies, operational strategies to reduce CO2 emissions, make it a bit more energy efficient. And as well, we want to make SmartSquare. SmartSquare is an area of the campus. I'm going to explain the next slides. We want to make it a bit more smart and flexible. We can possibly detach it from the rest of the campus, and the decisions that we take in how to operate it, they can be used to this area of buildings and see how they work. And maybe if we see that there is a good energy efficiency happening there, we can expand those to other areas of the campus. And as well, the Warwick standard is reducing heat demand in operation through better building standards, better construction, better running of the buildings. So there is this project which is finalizing. So we have funding from BASE to run a heat network delivery unit, look at the whole campus and see what the consumption of the whole campus is, how we expect it's going to evolve in the next few years, and try to provide all that heat that is needed with vapor compression heat pumps. So yeah, replacing, as I mentioned earlier, the main energy center. We have one here in the middle of the campus, and we have another one here outside of the campus. So we want to electrify the heating, and we also take into account some solar energy, renewable energy that we get from PV. And so I think they should publish their results soon. So that's one project. And then the next one is me, which I've been looking at the SmartSquare. So what is a SmartSquare? As we can see, this is the whole campus, and a SmartSquare is these buildings that are here in this area that are basically connected to the same line of the district heating network. So they represent around 10% of the campus energy consumption. They are fairly new buildings. I think the oldest one is maybe 30 years, the newest one is 3 years old. The standard of the buildings are quite good, and they have good building management systems installed. So I guess it's easy to monitor or collect energy data from them. Basically, we want to see what we can do with this area, electrify the heating, and then probably expand to the rest of the campus. We want to reduce cost and carbon CO2 emissions. The analysis that I've been doing in SmartSquare is mainly technical. It's empirical, as I've been collecting data in order to understand how the buildings behave. Then I'm going to, the next step of my project is going to be to analyze heat pump options to decarbonize SmartSquare. But in the meantime, we're going to start trying different things and see how the buildings react to them in order to get to the final stage. We would be, now we are happy with how the building is behaving. We think that we can now electrify the heat and it's going to have a good efficiency. So this is SmartSquare. We have a bit of a mixture of different types of building. So we are a university campus, so we have some residential buildings here. We have 3 residential buildings. We have 3 car parks, but we don't really, I'm not analyzing them as they don't have heating delivered to them. And then we have these other, the orange star buildings, which are non-residential. They're mainly labs, teaching, and offices. So there are 17 buildings. As I said, the oldest is around 30 years. The youngest, the newest is 2 years old or 3 years old. And I've been analyzing the power use, heating, cooling use, the production of PV, and also we can measure as well electrical vehicle consumption. So this is what I've been gathering: heating consumption, daily, hourly, PV production, cooling consumption, electricity consumption, gas consumption. We have some buildings that are being heated at the moment by gas. So very important internal temperatures of the buildings. Then we also measure the primary circuit mass flow. We have the temperatures of the primary network, the flow and return temperatures, and some of the buildings are connected directly to the network. Some others have a secondary circuits in them, so we can measure those temperatures as well. As I said earlier, more or less 50-50 divide between electricity and heating consumption. We have a heat pump, one heat pump installed in one of the buildings. The rest is just energy use in lighting, laboratory equipment, etc. Most of the energy comes from CHP plants. We have some PV production, but it's really small. When analyzing the heating consumption in the buildings, I had to differentiate between space heating and domestic hot water. So I'm basically, from now on, I'm going to be focusing basically on space heating. Domestic hot water, because the delivery temperature has to have a certain temperature because of health issues, health and safety. That can be provided by point of use heaters, and then we can leave space heating to heat pumps. Yeah, this is how at the moment looks like the provision. Most of three-quarters of the heating comes from district heating. We have some buildings use gas, one building use heat pump, and then point of use heaters for the domestic hot water. This is how the district network looks like. We have more than 150 buildings connected to it. But this is the part that interests me the most, which is the branch where the SmartSquare buildings are attached to. So we have flow at the moment of between 75 and 85, and the return is between 50 and 65 degrees. First of all, I look at the buildings, what the performance is according to the CFD energy benchmark. And we see that most of them are good. And in the green part, some of them maybe need some work on, and 2 of them, they didn't perform really well. But for example, we need to be careful as well with the type of building that we are working with, because phytobiology, for example, they run experiments. I think it's basically a big greenhouse. So we cannot really reduce much the energy that they need, the energy they use, because they need it to run experiments. But the other buildings, maybe we can intervene and come with energy efficient solutions for them. I started collecting data and basically relating how the buildings, the energy consumption of the buildings with the outdoor temperatures, seeing if there are seasonal or daily profiles that can be useful in the analysis. So for example, some buildings during the weekends, they shut, they don't get any heating. Some others, as for example, this is a residential building. This building needs to be heated up every day of the year because they have people living there all the time. So I've been modeling the space heating according to the outdoor temperature. I also model it with the heating degree days and seeing that between both models, the consumption is very similar. I've also produced heating profiles of the days of the week in blue and the weekends across a whole year to see where the peaks are. There have been identified some gaps in the data because, well, it's not perfect. So sometimes there is a problem in the data reading and gathering. So with these profiles, the calculating the space heating according to the outdoor temperature, I could fill those gaps and have a better data collection. This other type of data that I've been gathering, as I said, temperatures of the heat district network, primary and secondary circuits. I've also identified that in some cases, the solar radiation plays an important part in the heating of the buildings. So I wrote script and ran some simulations and could identify I call it solar factor, but it's the effect that solar radiation has in the heating of the buildings. So as we can see here, without solar factor, the temperature line was quite far away from what it was recorded in the building management system. So I'm quite happy with that. So a few tiny things I've been introducing in the model. I've also modeled the UA value, heat transmittance of the buildings, and the thermal mass of the buildings in order to model them, simulate them. So here we can see what the temperature of the buildings are. This is my simulation according to the gathered data of heat consumption in the buildings. So as we can see, again, without solar factor, it was with solar factor, looks a bit more stable, around 21 degrees. That is the temperature we think the buildings are set to. Then I've been liaising with State's Department, and we have some intervention options that we want to try in the buildings. And it's especially important now that we are starting the heating season. So we want to, first of all, reduce peaks, which means we probably need to increase the operational hours. So we see different profiles of the buildings across a week. This is how much energy they consume in a week. So we see these peaks early in the morning, heating starts, and we see this big spike in the power required. So for example, these buildings would need to maybe have a constant delivery of energy to them in order to avoid these peaks, or maybe start a bit earlier the heating. Other buildings are fairly stable throughout. So by doing this, by doing constant heating of the building, we see that the energy consumed by the building is more or less the same, but the reduction in the power needed goes from 0.35 to 0.15. So it's quite a big reduction. That's very important if we want to replace the heating provision by heat pumps to reduce the big powers to the network. As well, I ran 3 simulations. Instead of keeping the buildings at 21 degrees, what happens if we decrease the internal temperature of the buildings? And I observed that there is a drop of 8% of the energy consumption by each degree that we reduce the internal temperature of the buildings. And another intervention we could do is reduce the secondary circuit temperature. So in this case, for example, if I start reducing the temperature of the secondary circuit in the building, the power is going to start reducing, and there is a limit where the building says, well, I cannot cope with it. And as we can see here, and the internal temperature of the building starts dropping from 21 degrees, that was the set point, starts dropping even below 19, and then is not acceptable anymore. So we can see here, the secondary flow temperature originally was 80 flow, 60 return. If I start dropping it, reaches a point where it cannot cope with it. So it's good to analyze different buildings. For example, this other building copes really well. This is a newer building, and it's good to identify different temperatures where the buildings can go. And that's it for me. Basically, I'm going to run some experiments, varying different heating to the buildings, monitor those experiments, and then incorporate my findings into the modeling in order to then introduce heat pumps and storage and develop an economical model for SmartSquare.
Thank you very much. Thank you very much for that.